right, guys, the next thing we're going to talk about is salts and how they can actually affect the pH of water. And this is going to become very important because as we progress through this unit, we're going to start having acids and salts, or bases and salts, all mixed together to create something called a buffer system, and that's going to affect our calculations. So we've got to understand the nature of salts first to kind of be able to work through that process. Okay, and this is going to affect us in titrations as well. So what is a salt? A salt is nothing more than a ionic compound or anionic compound. That's all they are. It's a metal plus a nonmetal, or a metal plus a polyatomic ion, or in reality, it's a cation plus anion if we're going to be very specific with our definition here. So it's really something we're very comfortable with. When we take a salt and dissolve it in water, if that salt does dissolve, and as we'll find out later in this unit, all salts do dissolve to some extent or another. Sometimes it's a very, very small percentage, sometimes it's a big percentage. Those ions floating around in the water can interact with water to produce a basic or acidic solution, okay? And what we're going to do is I'm going to go through and kind of look at some of these and see if we can figure out how and why this is happening. So we kind of got four categories here. And remember, we're looking at a full salt. So we've got cations and anions. And a cation and an anion are both produced from a salt when it dissolves. And what we're looking at is, are these anions and cations from strong or weak acids and strong or weak bases? So just kind of scrolling down here a little bit, let's work through some of these and actually see what's going on. Okay, let's say I take sodium chloride and I put it in water. Well, we know sodium chloride is fully soluble, which means when it dissolves, it's going to break into sodium ions and chlorine ions completely. There's no question on that. It dissolves completely. There's no sodium chloride left. It's sodium and chloride ions floating around, and that's it. Well, these guys are floating around in water. So then we can have a secondary reaction of these guys with water. Now, this gets a little bit interesting, but just kind of follow along here. We know water can be broken down into HOH, also a cation, hydrogen positive, anion, OH negative. Well, sodium's positive, who's it going to be attracted to? It's going to be attracted to the hydroxide ion. And remember, water's going to be dissociated, so these hydroxide ions, to some extent, a very small extent, 10 to the negative 7th, are going to be floating around anyways. Well, sodium could bond with hydroxide. Now, the question is, this can happen, but does it actually happen? And the answer is no. Think about it for a second. Will sodium hydroxide form in solution? And the answer is no, because this guy is a strong base. Even if it did form in solution, it would immediately dissociate into sodium and hydroxide. So it can't reform in solution. This reaction will not occur. Okay, same with this guy down here. If we look at it, again, HOH, chlorine steals the hydrogen, forming HCl, and technically hydroxide, because that's the leftover up here. We would have sodium hydroxide plus hydrogen ions if this reaction occurred, and again, it doesn't. HCl is also a strong acid, or a strong substance, so it's not going to form either. If it did, it would immediately dissociate, and we'd reestablish equilibrium based off of our water. So when the ions come from a strong acid or base, meaning they are the conjugates of a strong acid or a strong base, they're what's formed after a strong acid or strong base has dissociated, or what could form after a strong acid, strong base dissociates. These guys will not affect the pH of the solution at all. So if I take sodium chloride and put it in water, my pH is going to equal 7. In other words, the only thing affecting pH in this system is going to be my water equation, which is breaking into hydrogen and hydroxide equally, according to Kw, which is 10 to the negative 7th. So sodium and chlorine aren't affecting that solution at all, so pH doesn't change. Okay, but what happens when we put something in that isn't from a strong, or isn't a conjugate of a strong or weak? Or sorry, isn't a conjugate of a strong acid or a strong base. There we go. Let's say we put sodium fluoride into our solution. Okay, so we have NaF. Also a fully soluble salt. It is going to dissociate completely into sodium ions and fluorine ions. Now, we already talked about sodium ions. Sodium ions aren't going to interact with water because if they did, they would just form sodium hydroxide and hydrogen ions, and then sodium hydroxide associates completely and does nothing. Okay, so what that leaves in solution that could possibly interact with the water is our fluorine ion. So what would fluorine ion do? Well, if I've got it interacting with water, we know it's not going to reform with sodium because if it did, it would dissociate completely. So again, this equilibrium, this very, very heavy this way, it will not reform this. This guy is gone. So it's staying as sodium ions, it's staying as fluorine ions. So the only other substance in solution is water. And that's what makes it a solution, or an aqueous solution anyways. So what happens here? This negative is going to steal a hydrogen from water, forming HF and hydroxide ions, what's left over. So now the question is, will HF form in solution? Can it form in solution? And the answer is yes. Why? Because this is a weak acid. A weak acid can and will form in solution, whereas a strong acid or a strong base will not, because if it did, it would dissociate completely. Like it's not able to, that equilibrium is shifted so far towards that dissociated side, it can't reform. But a weak acid, because the dissociation is actually shifted so far towards the reactants, it can and will form if the availability is there in solution. So what does this actually mean for pH? What this means is we have hydroxide ions forming in solution. And as they're forming in solution, that's going to make our pH basically basic. So let's change this instead of equal to. We're just going to say pH is going to be greater than 7. It's going to be a basic solution. And I know that's a little bit weird because you're saying, but there's an acid here. You're right, but the formation of the acid is producing the hydroxide ion. This hydroxide ion is causing the pH to be greater than 7. HF is actually not dissociating here. It's forming versus dissociating. And if it did dissociate, it would form back into H2O and fluorine ions versus hydrogen ions and fluorine ions. So it's kind of looking at that equilibrium here. And because, again, we have the secondary equilibrium of H2O going on at all times, because we are always in aqueous solutions for our acid bases, it is this concentration increase of our hydroxide ions that is causing the formation. So hydrogen ions are decreasing because hydroxide ions are increasing in this equation, and that's what's making the solution actually basic. Okay, so what does that mean? That means a conjugate base of a weak acid will cause the pH to be more basic. So an anion of a weak acid raises the pH, makes it more basic. Let's look at a cation from a weak base. And really our predominant one we'll see here, at least in simplicity's sake, is ammonium. So let's say I have ammonium chloride, which is NH4Cl. Again, fully dissociable or soluble salt, so it's going to dissociate into ammonium and chlorine ions. And again, it's going to be completely shifted towards products. There are going to be no reactants left over. It is nothing but ammonium and chlorine. And we've already talked about chlorine. Chlorine is not going to be able to steal the hydrogen from water because, again, if we think HCl, that equilibrium is shifted so far towards this side of the equation that this cannot form in solution. It's a physical impossibility. Chlorine is not strong enough because HCl is such a strong acid. Its conjugate base is so weak, it cannot steal the hydrogen from anything to reform HCl. So if you kind of remember that comparison. However, ammonium, if we look at him, is a weak conjugate acid. He came from a weak base. So when he interacts with water, what is he going to do? Well, acids give up hydrogen. So we end up forming hydronium and ammonia in solution. So what does this do to our pH? Well, we have the formation of hydronium ions. And as hydronium ions are forming, hydroxide ions are decreasing in solution, because again, remember, we do have this reaction going on. at all times as well. Okay, so as this is increasing, this is decreasing, so our solution is becoming more acidic, so our pH is going to be less than 7. So this is the analysis we have to do, and it's a little time consuming. It takes a little bit of work to go through and look at it and say, okay, I have a salt. Does the salt affect pH? Possibly. Then we have to look at the ions of the salt and figure out, do those ions, are they conjugates from strong acids or strong bases? So, like again, a conjugate from a strong base might be something like sodium. Okay, and really not technically a conjugate because he fits in the Arrhenius model more than the Bronsted-Lowry, but we get our point. Or is he a conjugate from a strong acid like chlorine? Or is he a conjugate from a weak base, so like NH4, or a weak acid? And that's what we have to go through and look at and kind of say, okay, will these interact with water in such a way where pH will be affected? If they are ions that came from or are conjugates of, I should say, strong acids, strong bases, they have no effect on our pH whatsoever. But if they are ions that could be considered conjugates of weak acids or weak bases, they will affect our pH. We then have to go through and think about what they're doing. Are they donating a hydrogen like the ammonium ion, or are they stealing a hydrogen like the fluoride ion? And then determine what's happening. And I would always rewrite that secondary reaction to be able to see what's going on here. All right, what we're going to do in the next video is actually do some calculations with salt. So we've talked about what a salt is and how it can affect pH. Now we have to calculate actually how it affects pH, like what pH does a salt give us. And again, that's just like everything based off of molarity of the salt that's present and the equilibrium of said salt. So that's what we're going to look at in the next video. Thanks, guys.